Okay, so we're going to get started. We have Iddo Drori from YU, uptown a little, speaking about AI for superhuman math.
Okay. Thank you. So, first of all, there are two online apps that are available via these QR codes. Um, so they're follow-up and data and other supplementary material to this talk. So you can take a picture and look at that offline or online. Okay, so my agenda for today is to talk about AI coding and agents for mathematics, formal verification in mathematics, AI and human collaboration in mathematical research, and specifically I'll focus on the IMO, Putnam, and Erdos problems. Okay, and so our roadmap is to talk about AI in math research that is shifting from generation to generation and verification to agentic workflows or agents and harnesses to human AI co-discovery with formal proofs. Okay, so just a bit about introduction or the timeline. AI coding and agents for mathematics have evolved in the past 3-4 years. We've started out with training models by self-supervised learning and fine-tuning them on code, and then using that to solve mathematical problems, very simple ones. Then these models were trained by reinforcement learning with verifiable rewards. These are the reasoning models, etc. Then moving on in test time training by reinforcement learning or evolutionary program per problem, per specific mathematical question, once the question is actually posed. And nowadays we're in the stage of AI agents with formal verification that are used with harnesses and agents. So think about 25, at the beginning of 25, we had coding and AI coding assisted. By the end of 25, usually you use an AI for coding. There's a shift for proving. So if we call this vibe coding, we call in mathematics vibe proving. And a similar shift has happened in mathematics, which is quite dramatic in the past 6 months, in the past 2 months, etc., and over research in particular. And so in 2022, when we started moving from just text-based LLMs to program synthesis and execution, these LLMs that were self-supervised, trained, and fine-tuned on code, having them write programs and do simulations moved the needle overnight from 8% to 80% on a standard math benchmark. That's in 2022. Following year, in 2023, 2024, the O1, R1 models came out, OpenAI O1, DeepSeek R1. Essentially, the famous picture with the self-supervised learning, which is the cake, and the cherry on top is the RL, was turned on its head, and we had the cake smaller than the cherry. The cherry was the reinforcement learning on the right. And this means that the model essentially has a checker, and math is something we can verify. We can have a perfect verifier and perfectly verify that the solution is correct, complete, convincing, etc., and not muddy the water by introducing false positives into our training set, etc. Okay, and so the key idea in these language reasoning models was a loop of reinforcement learning where we had a perfect verifier that could verify the answer. And then we can run this loop over and over again and optimize and train the model. Following that, we started working with test time, reinforcement learning and test time coding. Here's an example from 24. This is a problem 5 from IMO 24. It's called Turbo the Snail. The idea is that you have Turbo starting from the top row of this game, and he needs to get to the bottom row of this game. But there are hidden monsters in almost all of the columns except for one of the columns, and he doesn't know where the monsters are, but he knows that there's exactly one monster per row, except the first row and the last row, and that each column contains at most one monster. And the question is, how does this character go from the top row to the bottom row without hitting the monsters, and how many attempts does it take to do that? Okay, and if you look at simple LLMs at the time, they would come up with an answer. Well, try all the columns and figure out a column that's empty and do that. If you train this in test time by building an RL model and training it in test time, then it would actually find a solution that is the following. We would go, for example, to the top left and then do a scanline sweep on the first row until we hit the first monster. There's guaranteed to be a monster. It's in red here. We're looking at the image on the left. We hit the monster, so now we know it exists. But then that's our first attempt. We go back to the first row. Now that we know that there's a monster in the first row, we know that that's the only monster in that first row. We can use that fact to go in the second attempt, and just before hitting the monster again, go down to the second row. Okay? If we're lucky, there's nothing there. If there is nothing there, then we can go right, and since there is one monster per column, that monster on the left is essentially guaranteeing that the entire column is empty. We can go all the way down, and we're done. But if that's not the case, then we hit a second monster on the second row, as denoted here in red, and then on the third attempt, we can go to the right of the first monster, go left, because it's free, because we know where the second row monster is already there, and then go down all the way. 2 attempts. In the worst case, we need a staircase pattern going right and down, right and down. If we hit a monster on this path, then based on that monster, we can go all the way to the left and then all the way down. Okay, so essentially, the algorithm, given the problem, trains in real time a reinforcement learning model. The reinforcement learning model figures out the answer, and once it gets the answer right, it proceeds to use the answer to start writing a proof. Okay, now in some of these cases, finding the answer is easy and proving is hard, and the IMO is a proof-based competition. But in other cases, finding the answer is hard as well, and not just the proof. In IMO 2025, problem 6 was such a case. There was a grid of unit squares, and we needed to place a grid on this unit square. So essentially, there is a grid of 2025 by 2025. That's the resolution. And the idea is to place a grid of rectangles such that each and every tile lies on a grid line, and every unit square is covered by at most one tile. And the question is, what is the minimum number of tiles that we can place on each row and each column of the grid so that it has exactly one unit square and not covered by any tile? So, the first thing you see here is that in every row and column, there is a hole. They're denoted here in black, and we need to cover this plane with rectangles. Essentially, it's a tiling problem. And if you think about this, and you think about these holes, they're essentially a permutation of the numbers 1 through n. And the model needs to figure out how to create this tiling. The optimal tiling for this example is on the right. The problem with this optimal tiling is that in this case, just in this case, here's the 4x4 example where we have 5 tiles. Here's the next up, here's the 9x9, etc. So there is an equation that scales up, which is the minimum number of tiles. The problem is, in order to find, using a simulation, this instance, which is the third largest instance, it would take computationally several years for a laptop machine to compute. It's combinatorically exponential. So it's very hard to find this answer, and it's actually almost infeasible. So let's discuss what happened and how this story evolved. Okay, so on the day of the IMO, I was there representing, and essentially we used Claude and Gemini once the question was released, and Claude and Gemini and all the models got the answer wrong. They all got the answer, which was the diagonal, which in the case of 2025, by 2025 was 4,048 holes and their positions and the rectangles around these holes. But looking at this problem, the year is 2025. 2025 is not just a number, it's the square of 45. Suddenly, you look at the problem with human intuition, you realize that right away, in a few seconds, it's 45 square. And then you say, well, okay, you give the model a hint and you say, what about 45 square? Can you check that out? And if you proved it there and then live, this was actually captured in Australia at the IMO live, right when the questions were given. The model is able to do the tiling, to find it out. But on 60 other runs, it does not, okay? It needed that extra human touch, and therefore none of the models were able to solve this reliably, okay? So fast forward a few months, and now we can solve this reliably given all of the models. And what is the method? The methodology is evolutionary programming. You evolve programs. You have the models write code, and this time, instead of just writing code for simulation or writing code for RL, you have it write evolutionary programs that improve and have some fitness function, and these programs improve after a few generations, and for this instance, it finds the answer. Now, once it found the answer for this instance, and it has 3 instances, 3 points are not on a single line, it can find the equation. Once it has the equation, it can prove the result. Okay, so what's a story behind this? When running this, so we were running this with one of my PhD students, and what happened was that the model initially said, okay, I'm going to search 24 functions, classes, and search the hyperparameters of these functions with genetic programming to find the correct function, okay? And then it actually did a really long search. It found the function family, then it found its parameters, right? Because this has a parametric form. And then it says, here's the answer. But then when we looked carefully at the code, it actually used the answer for the 3rd instance, which was computationally infeasible. So it had tricked us. You know, we found out that the model was tricking us by using that, creating a whole facade of 20 families of functions, doing the whole search, doing the whole genetic thing, algorithm, and presenting to us the result. Haha, I found it. Okay, so because we were experts on this problem, we figured that out, found that out, removed that, and did a clean run. And in a clean run, now there are multiple OpenEvolve, Shinka Evolve, Theta Evolve, etc., and multiple communities, both the optimization community, Evocuts, etc., that can reliably answer this question. Once you reliably answer for small instances, then you find the equation. Once the equation is found, the proof falls. Okay. So what is happening here? We have AI now, and following these examples, we've moved to a realm where we can also generate formal proofs. We can translate from natural language to Lean, which is the language of mathematics, and translate back. And if you think about it, formal proof and formal verification is something super important for us in order to verify that automatically that the proof is correct. And when you hear about these agentic harnesses or these experimental versions of these models, essentially think about cloud code using tools or OpenAI Codex app using tools that are specific to Lean, which is the formal language for mathematics, one of the formal language. The tools can be search, can be natural language generator verifier, which we heard earlier today, can be different, which is a set of prompts essentially, and different tools that are related to Lean for finding, searching for lemmas, and combining and solving sorry statements. Okay, so essentially, if I do a show of hands here, how many here are using Cloud Code or Codex and Vibe coding or using AI for coding? The same answer would be probably correct, should be correct to how many of you are using AI this way for math. Okay, the harness is the same. Cloud Code is not just limited for writing code, it can do math. And the difference is the tools, the command line tools, the MCP tools that it uses. And in the same way that it has subagents, and you start Cloud Code with /init and best practice, and then use a setup code plugin, and then use a superpowers plugin, and then use an MD management plugin. Essentially, if you use Cloud Code correctly, or Codex or any other Gemini CLI, all of these CLIs correctly, you understand the power of them to actually act and not just give advice. Okay, they actually do useful things. And whether it's in coding or in math, that is another thing. And so, sure. Sure.
So, I guess I understand that with something like Cloud Code, you ask it to produce code and it does something for you, right? And so you're envisioning a context where you ask one of these things, so you're saying that it should produce improvements.
So let's flip it around. These agents have plugins and capabilities. They're literally called superpower, and they interrogate you, the mathematician, and they ask you the questions. You bring it a conjecture, an open conjecture, and it starts asking you many, many questions. Like an interview of questions, like 10, 15 questions. That's the strength of this AI expert mathematician collaboration. So we have these agents asking our mathematicians questions, and they answer, and then they say, wow, I thought about this direction. I did. That doesn't mean that it will get the proof, but at least it gathers the information first. Okay. Yeah. And the tiling, it proceeded by an evolutionary algorithm. It created, the evolutionary algorithm is well known. It's an open GitHub package. It used it and ran it. The harness that used the GitHub package with the problem and created it. And we needed to verify and look deeply into the code to verify that it wasn't cheating or doing anything that was not kosher. Well, I will get to that. Okay. And so these formal agents, essentially formal proof agents, started to be open sourced. Apple researchers released Hilbert ML, one of these open source, and then Numina Lean Agent also released an open source formal verifier that you can download and check. And in parallel, Harmonic released Aristotle, which is a closed form agent that uses natural language and formal proofs and these tools. ByteDance Seed Prover, Axiom, which had a conjecture the other day, Aleph Prover as well. What happened is that the open systems closed the gap on the closed systems. So what's valued and closed is now open and free for everyone to download. So you can actually look at the benchmark and you can see that this grew exponentially. So to your question, you can actually try it yourself. You can go and download, run it on this program, and actually verify. And so there is absolutely no reason not to verify today. This used to be a barrier to entry. But if you are getting an answer from an AI, and sometimes you say, well, is it correct or incorrect? I need to bring in a mathematician. There's a turnaround time. The mathematician will verify, will check. Right now, there's no excuse for us not to formally verify it. Okay, this is the state of the art. Yeah.
640 problem solved. Holland River solved 668.
Well, yeah, that's yeah. No, there's 672 in this Putnam bench, all in all. 672 they took out of, we took all 1031, all of them, and subset is 672. Aleph did 668. You can look at Numina. It's an open source lean agent. It solves all 2025 Putnam, everything. Okay? So what happened here, there was this unequilibrium where you had closed source, essentially agents. They were using harnesses. Essentially, it's cloud code plus formal verifiers plus lean. Okay? That's similar to that. That's what these things are. And once Apple released their source, months later, these provers sprouted, and this equilibrium was kind of dissipated. Okay. Now, nowadays, people prove results that are obtained in conjunction with AI models and agents and related tools. For example, Ravi Vakil's latest paper. And that is the framing of how these conjectures or results are proven in conjunction with AI. Okay. Essentially, we are in an era of iterative vibe proving and verification, because when you're vibe proving, you have the tools to verify, and you can check. The AI agent asks questions, and then formally proves and verifies in lean, and then you iterate. And so usually the iterations are separating the problem into small chunks or pieces, etc., or refining and iterating. It's an iterative process, like you code, in the same way you code in application. Very similar. That's a similar feeling, that you have an expert mathematician who is vibe proving using this tool. And in the same way where you have in Python unit tests, or if you're doing electrical engineering, you have FPGA and you can test. Math has a language. Fortunately, this language is being evolved, and the number of primitives in lean are increasing to handle larger and larger scope. This was the bottleneck, essentially. The bottleneck was that in Python, where we have millions of lines of code and everything is well defined, in mathematics, lean was kind of smaller, millions, and way smaller, and not all the definitions were in place. And now they are in place, an increasing number. And so this has become open, and there's an entire ecosystem of people using these tools to prove things. Yeah, I will get into these categories. It's a great question. And I think that because there are so many results, eventually, this is probably leave a bit to the panel, eventually peer review in mathematics may require formal verification. Why not verify, right, if you can, and do that. And so if we look at the last 60 days, these are the open Erdos problems that have been solved with AI, with these methods, according to the Erdos problem database with Terence Tubb. Okay? He's maintaining which is solved and which is not, and which is partially solved and which is formalized. Okay? So this process, if we look at the last 60 days compared to the last 6 years, this is a lot of progress, and these are really open problems. So a bit about a field journey in the IMO. I was physically at the IMO at the Sunshine Coast, representing a team from MIT, Stanford, and Columbia. And around the table were teams from Google and teams from ByteDance, 2 US companies, 2 Chinese companies, and 1 person representing academia. Okay? Getting the problems live. And you can see the kangaroos there on the Olympic Village jumping around, where the students were kind of walking around. Beautiful place. Was a very nice atmosphere. Okay? And the goal was to use AI to solve these problems. Okay? And giving a talk to the 700 students, I posed questions like, how can we use AI to solve IMO problems? How can students interested in improving their problem-solving skills use these models to prepare for the IMO? They need sources of problems, they need a solution checker, and they need some type of guidance and mentorship. The IMO has different problem categories. It's a high school competition: algebra, geometry, number theory, combinatorics. This is all the 398 problems over 66 years. We took all of the problems over all of the years, no exception. There are subcategories. You can look at all the detail of these subcategories, etc. And the performance is striking. If you look at the human performance from the official IMO statistics over all 66 years and compare that to recent models, you get a striking picture of their performance, okay? And so if in July, multiple models, natural language and formal, could solve 5 out of 6 problems perfectly, now with current models and evolution programming, you get 42 out of 42 points, okay? All questions. It's really important to evaluate this correctly. We do cross-model family evaluation, so we have one model solve and one model, another family of model evaluate. If we have GPT solve, we have Gemini evaluate, and Gemini solve and GPT evaluate. We use the same prompt that has been shown to be highly correlated with rigorous human expert grading of 15 medalists from the IMO. And we also check for leakage. Were these problems leaked or not? And I'll explain how we do that. And so you can see that if you give the same model, Gemini, the privilege of grading itself, it has some bias. If you give GPT to grade Gemini, that's better practice, of course. Perhaps more strikingly, we look at the problems, we split each of the problem to a prefix and suffix, like what are the conditions of the problem and what needs to be proven, and ask the model if it can predict the suffix from the prefix, right? And if it can, if it really hits on the nose that it needs to determine the minimum rather than maximum or verbatim, then we know that it's leaked, we mark it leaked, okay? And so we check leakage of all the problems across all the IMOs in all the years. And you can see that different models have different, you can call it leakage or use the IMO in their training data differently. You can see that Gemini uses almost 300 out of the 398 of the problems in its training, whereas GPT uses about 50. This is a striking difference.
By leakage, you mean somebody wrote down a solution 30 years ago.
And exactly, and trains on it and whatnot, right? And the problem, and we check that, and we do this cross-model family evaluation to check for the leakage, okay? And then we look at the clean problems, but still the picture is the same. AI compared to humans only on the clean problems, and we still see a significant improvement. We look at the leakage through all the years, and you can see in the recent years leakage, like you can see how many clean problems and leak problems. We look at the leakage across 55 languages, because these problems are provided in 55 languages. The diversity of the students is amazing. 110 countries, 700 kids. They speak 55 different languages. The questions are given to them in their native language. They think in their native language really quickly and more naturally than translating, so they don't need to do that translation. But we take into account that this can be leaked in many places in the world. And so we do the analysis across all the 55 languages, and we actually get a world map of the leakage across 66 years of the IMO questions, and we can run this through time. This is for 2025. Turned out Korea leaked a problem or two, but essentially you can run this map through time and evaluate the LLM leakage across the globe in different languages through time. And the results are that the AI performs substantially better than the humans. People mentioned gold medal level performance. We do want to give the students that won these medals, it's their time to shine, not the AI. So of course we defer the research rather than announce these things. But these are the results that AI now has. And this is across categories. You can see combinatorics is usually harder than the other categories, both for AI and humans. But now that we have all this data, we have all the human solutions from 66 years to all the problems and all the AI solutions. And we can look at all these solutions and all of these problems. And it's really interesting to see what humans and what AIs do and what are their solution approaches. And so in geometry, you see humans, the AI uses coordinates because it's computational. Humans use angle chasing, okay? So now we can actually say, where are these alien moves for these solutions coming from for AI, or these elegant and novel proofs, which is probably the most interesting part, is to find new solutions, novel, simple solutions that are more elegant by AI. And this demonstrates simple and novel solutions. And so the way human and AI approach these questions, and it's all available on the app. You can look at all of these, all of the data. Due to lack of time, I won't go into the details. You can see that these approaches are substantially different. Humans still have a diverse set of techniques and solution techniques. That is interesting. And we can actually look at even more insightful metrics about proof lengths and abstraction levels and technique diversity and insight of different AI models and humans, and measure that reliably. And then we can also compare natural language to different formal provers. ByteDance has a formal prover which had thousands and thousands of lean lines. Aristotle was more elegant and modular, and we can compare these different formal provers to each other and the natural language proofs to themselves. And so we can look at proof novelty and elegance and learn from that. And of course, measure the time it takes. We did this to all IMO questions over all the years, all Putnam questions from 1938, and all IMC. Putnam is an undergrad competition. In the US, IMC is the corresponding global one. And so we looked at all problems through all years in all three competitions and analyzed them all in different fields. So to wrap up, in conclusion, AI in math has shifted from just generating answers and benchmarking them to automatically benchmark. The benchmark, of course, was done automatically as well. Generating and verifying the proofs, super important in formal language. There's actually no reason why we shouldn't verify a proof nowadays. To agentic workflow, so think about working with Claude Code instead of coding for proving. Or your favorite CLI, Gemini, or Codex, etc. And now we're in a really wonderful age of human AI co-discovery with formal proofs, where humans and AI every other day, we see another conjecture, open problem, etc. Being proven, which is, I think, wonderful and great for the field and allows us to move further and advance mathematical research. With that, I'll thank you and take any questions.